Let us find the HCF and LCM of the numbers 8, 9, and 25. The prime factorizations are 8 equals 2 cubed, 9 equals 3 squared, 25 equals 5 squared. Notice that 8, 9, and 25 are powers of 3 completely different primes, 2, 3, and 5 respectively. There is no prime factor common to any two of these numbers. Therefore, the highest common factor of 8, 9, and 25 equals 1. On the right, for the lowest common multiple, we take all three highest powers. LCM equals 2 cubed, times 3 squared, times 5 squared. That is 8 times 9 times 25, which equals 1800. Exercise 1.1, question 6. Explain why 7 times 11 times 13, plus 13, is a composite number. We look at the expression, 7 times 11 times 13, plus 13. Notice that 13 appears as a factor in both terms. We factor out the common number 13, the expression equals 13 times the quantity 7 times 11 plus 1. Simplifying inside the brackets, 7 times 11 equals 77, and 77 plus 1 equals 78. So the expression equals 13 times 78. A composite number is one that has factors other than 1 and itself. Since this number equals 13 times 78, it has 13 and 78 as factors. Therefore, 7 times 11 times 13 plus 13 is clearly a composite number. Exercise 1.1, question 7. Sonia takes 18 minutes to complete one lap of a circular track. Ravi takes 12 minutes for one lap. If they both start at the same point at the same time, after how many minutes will they next meet at the starting point? To find when two repeating events coincide again, we need the least common multiple of their cycle times. Sonia completes laps at 18, 36, 54 minutes, and so on. Ravi completes laps at 12, 24, 36, 48 minutes, and so on. The first time both sequences share a value is 36 minutes. We can see this highlighted on screen. The LCM of 18 and 12 equals 36. Therefore, Sonia and Ravi will meet again at the starting point after 36 minutes. Exercise 1.2, question 1. Prove that the square root of 5 is irrational. We use the method of contradiction. Assume root 5 is rational. Write it as a over b, where a and b are coprime integers. Squaring both sides, 5 equals a squared over b squared. This gives 5b squared equals a squared. Therefore, a squared is divisible by 5. By Theorem 1.2, since 5 divides a squared, 5 must also divide a. Let a equal 5c for some integer c substituting. 5b squared equals 25c squared, so b squared equals 5c squared. Now b squared is divisible by 5, so b is also divisible by 5. But both a and b being divisible by 5 contradicts our assumption that they are coprime. Therefore, the square root of 5 is irrational. Exercise 1.2, question 2. Prove that 3 plus 2 times the square root of 5 is irrational. We use the method of contradiction. Assume 3 plus 2 root 5 is rational, and write it as a over b. So 3 plus 2 root 5 equals a over b. Rearranging to isolate root 5, subtract 3 from both sides, 2 root 5 equals a over b minus 3. Dividing by 2, root 5 equals a minus 3b, all divided by 2b. The right-hand side involves only integers a, b, 3, and 2. So the right-hand side is rational. This would force root 5 to be rational. But the square root of 5 is irrational. This is a contradiction. Therefore, 3 plus 2 times the square root of 5 is irrational. Question 3, part. I prove that 1 over the square root of 2 is irrational. We state the problem. Prove that 1 divided by root 2 is irrational. Assume the contrary. Suppose 1 over root 2 is rational. Then 1 over root 2 equals a over b, where a and b are coprime integers. Here is a useful algebraic trick: flip both sides of the equation. If 1 over root 2 equals a over b, then inverting gives root 2 equals b over a. Since a and b are integers, b over a is a rational number. This would make root 2 rational. But this directly contradicts the fact that root 2 is irrational. Therefore, our assumption was wrong. 1 over the square root of 2 is irrational. Exercise 1.2, question 3 part 2. Prove that 7 times the square root of 5 is irrational. Assume the contrary. Let 7 root 5 be rational, equal to a over b, where a and b are coprime integers. To isolate root 5, divide both sides by 7. Root 5 equals a over 7b. Notice, a, b, and 7 are all integers. So a over 7b is a rational number. This forces root 5 to be rational. But the square root of 5 is irrational. This is a contradiction. Therefore, 7 times the square root of 5 is irrational. Exercise 1.2, question 3 part 3. Prove that 6 plus the square root of 2 is irrational. Assume the contrary. Let 6 plus root 2 be rational, equal to a over b, where a and b are coprime integers. To isolate root 2, subtract 6 from both sides. Root 2 equals a over b, minus 6. The right-hand side involves only integers, a, b, and 6, so it is a rational number. This forces root 2 to be rational. But the square root of 2 is irrational. This is a contradiction. Therefore, 6 plus the square root of 2 is irrational. Theorem 1.2 is a crucial result that underpins all irrationality proofs. The theorem states, let p be a prime number. If p divides a squared, then p must also divide a. Let us verify with an example. Let a equal 12, so a squared equals 144. Let the prime p equal 3. Does 3 divide 144? Yes, 144 divided by 3 equals 48. Then by the theorem, 3 must also divide 12. And indeed, 12 divided by 3 equals 4. Confirmed. Why does this always work? If a has prime factors p1, p2, up to pn, then a squared has those same prime factors, each appearing twice. If prime p divides a squared, then p must be among those prime factors. Therefore p must also appear inner itself, meaning p divides a. This theorem is the key tool for every irrational number proof in this chapter. Theorem 1.3 proves that the square root of 2 is irrational. Step 1. Assume the opposite. Suppose root 2 is rational. Then root 2 equals a over b, where a and b are coprime, they have no common factors. Step 2. Square both sides. 2 equals a squared over b squared. Therefore, 2b squared equals a squared. This means a squared is even. Since a squared is even, a itself must be even. Let a equal 2c for some integer c. Step 3. Substitute a equals 2c. 2b squared equals the quantity 2c squared, which is 4c squared. Dividing both sides by 2, b squared equals 2c squared. So b squared is even, meaning b itself is also even. Step 4. We have found that both a and b are even, both divisible by 2. This means they share the common factor 2. But this contradicts our assumption that a and b are coprime. Conclusion: the square root of 2 must be irrational. This proof is the foundation of all irrationality results in this chapter.